Thank you very much. Good morning, everyone. My name is Simon. I will present our cross-disorder connectome study. In the background of the slide, you see the brain as a network of brain regions being connected by white matter pathways, providing efficient integration of information in the brain. However, in recent years, we have seen that studies showed that there are, in a wide range of brain disorders, white matter alterations. For example, studies showed that the backbone of the brain of the white matter connections is affected in schizophrenia. And there is segregation in the network in Alzheimer's disease. And also in ALS, people see that the white matter connections of the motor areas are affected. And so on. These results have been shown in a wide range of disorders. This has learned us a lot about the biological mechanisms underlying these disorders. But these studies most often focus on only one or two disorders. Therefore, they lack the power to identify which disconnectivity patterns are really disorder-specific and which patterns are shared across disorders. And that's strange, because we know from other modalities that there is indeed an overlap across disorders. For example, at the behavioral level, there is overlap in symptom pathology and there's comorbidity across disorders. And also, studies showed that some regions are vulnerable to gray matter abnormalities in general. And at the genetics level, there is a genetic correlation across disorders, and there is shared risk genes across disorders. So then if we go back to our white matter disconnectivity, could it also be that there is an overlap in the disconnectivity across disorders? It's suggested by reviews that it might especially be that there is a shared disconnectivity across disorders which reduces the efficiency of the brain, which reduces the integration of the brain. So it's now the hypothesis that it might be that the central connections in the brain, which are so important for the integration of information, that those connections are vulnerable to disease effects in general. To test this, we conducted a cross-disorder comparison. We compared the disconnectivity patterns across 12 disorders, including 8 psychiatric disorders and 4 neurological disorders, including schizophrenia, bipolar, ADHD, ASD, PTSD, major depressive disorder, obesity, OCD, Alzheimer's disease, MCI, ALS, and PLS. And PLS is also a motor neuron disorder. We collected MRI data and DTI data from our collaborators and open data sets, including in total 900 patients and more than 1,000 matched controls. And we reconstructed for all these subjects their connectome. We then compared these connectomes between the patients and controls within disorders to get for every disorder a disorder disconnectivity map, describing the reduction in fractional anisotropy between patients and controls. Then in every disorder disconnectivity map, we selected the top 20% connections with the highest, which were affected most as disorder involved. And we combined this into our cross-disorder involvement map, which describes for every connection how often it was considered involved in a disorder. So we took all the MRI and DTI data and we cut our cross-disorder involvement map, which looks like this. This is the map. And we could use this cross-disorder involvement map to then investigate whether indeed these central connections are in general vulnerable. To do that, we looked at 3 types of central connections. We looked at connections important for global integration, connections important for local integration, and spatial integration. We used 4 measures we used the edge removal effect on communicability and edge betweenness to measure the importance of connections for global integration, which is the importance of connections for the shortest path in the network and the almost shortest paths in the network. We looked at the edge removal effect on clustering to see their importance for local integration, and we looked at the wiring length. Then, for example, if we look at communicability, we calculated then, so for every connection, its importance for communicability. We took the 25% most central connections in this measure as central connections, and we combined the set of central connections with our cross-disorder involvement map to calculate their average cross-disorder involvement. We then compared this cross-disorder involvement with that which we obtained from a randomized disease effects map to see how high we would expect that the cross-disorder involvement would have been if there were randomized disease effects. So what we found is that indeed connections which are important for global integration and spatial integration show a higher cross-disorder involvement than connections than you would expect for randomized disease effects based on the permuted control and patient subject labels, whereas we saw no effect for clustering. We wanted to know further what was driving this effect and how this was in the brain. So we also looked at the backbone of the brain, which provides the shortest paths in the network and integration in the brain. So we looked at the rich club of the brain, which consists of the high degree regions and their connections. We looked at the three connection classes, the rich club connections between the rich club regions, the low feeder connections between the rich club and peripheral regions, and the local connections between the peripheral regions. And we found that indeed rich club connections, which are most important for the integration in the brain, show a higher cross-disorder involvement than feeder connections and local connections. So what we found is that indeed there is an overlap in the brain in the disconnectivity patterns across disorders, and that it's especially these central connections, they show a vulnerability to disease effects in general. So what we now did is we looked at the overlap across all disorders, and that was the first step. Next, we could also investigate whether there are maybe groups of disorders, for example, psychiatric and neurological disorders, which show an overlap in their disconnectivity patterns. And finally, we could use this information that we now have on the overlap across disorders to also see which disconnectivity patterns are unique to disorders. And we can use that information then to make biomarkers based on the MRI scans to diagnose these disorders also. I would like to thank my co-authors who contributed the data, who were very generous and made this study possible. Our funding and my colleagues from the Dutch Connectome Lab, 5 of them are here, and Martijn, our PI. Thank you very much.